So as promised in our last class, I said we are going to look into neutralization. So bring out your pen and write from definition first. Definition. So neutralization is the process in which an acid reacts with an appropriate amount of base to form salt and water. Acid reacts with base to form salt and water. Simply. Although we can define it in different ways, but this is the simplest one. For example, here this is an acid, this is a base. Acid base. So in each case, we are going to form salt and water. So before I extend this diagram, so first note that HCl is a strong acid, while sodium hydroxide here is a strong base. This is strong acid, while zinc hydroxide is weak base. This is a weak acid, this is a strong base, and this is a weak acid, this is a weak base. So during neutralization, it's either we have strong acid, strong base, or strong acid, weak acid, strong base, weak acid, weak base. How do we know which acid is strong? How do we know which one is weak? I've already explained that in my last class. I already gave examples of strong acid and weak acid, which you should know for some reasons. Now let's write the products for each. In this case, sodium is the cation here, chlorine is the anion here. So we are going to form sodium chloride plus water. Here, zinc with chlorine, that will be zinc chloride plus water. Why do we have two here? We've done that already when we did introduction to chemistry, the second lesson or third lesson. In this case, this cation here is going to come with, this, the anion here, the cation is actually H plus. The anion here is what? CH3COO minus. So what happens here is that this cation will come here, so at the end the salt form here is going to be CH3COO with calcium, but there will be 2 here. Because calcium is divalent plus water. So in this case, what are you going to have? So this ammonium ion will come with what? This carbonate. So you are going to have NH4 2 CO3 plus H2. So everything we have here are all salts. These are all salts, and they are all normal salts. So salts are either simple, compound, or complex. So they are all simple salts. Simple salts are either what? Normal salt, acid salt, or basic salt. So all the salts we have here are what? They are called normal salt. They are not acid salt, they are not basic salt. Although some of them are acidic and some are basic in nature, but we are coming to that later. So in short, this is what we call neutralization reaction. So let's see if the equation is balanced. So here, or let's see if they are balanced rather. So we have to balance. So in this case, we have 2 chlorine here, so we have to put 2 here to balance chlorine. And zinc is 1, so I think it's balanced that way. So in this case, I think everything is balanced. Yes. So for the next one, here we're having 2 of these, so we put 2 here. This is balanced. Calcium is 1, should be balanced. For the last one, NH4 is 2, so it should be balanced this way. So these are the balanced equation. Let me confirm if they are all balanced. So this one here is not balanced. Let's put 2 here. So I think with this it is balanced. Let's check for others too. I think they are all balanced now. So for the first one, 1 mole of hydrochloric acid reacts with 1 mole of sodium hydroxide to give us 1 mole of sodium chloride and 1 mole of water. Here, 2 moles of hydrochloric acid reacts with 1 mole of zinc hydroxide to give 1 mole of zinc chloride and 2 moles of water molecules. So same goes for all. So before I explain this, let's talk about this briefly. So how do you know if neutralization has occurred? So what we do is we pour a certain volume of base in a conical flask or in a beaker. So sometimes instead of having a beaker, you can have a conical flask. So instead of having this beaker here, you can have the conical flask here. For these 2 red dots, neglect it for now. If we add acid to base, what happens? The question is, yes, we know at the end of the day, there is going to be neutralization, salt to be formed. But if we add a particular amount of acid and it's too small, what happens? The solution or the compound, or let's say neutralization, will not fully occur. So before there can be neutralization, what happens? you have to add a particular volume or a specific volume of acid, and that volume of acid we usually call it the titer value. So if the volume is less, what happen? Neutralization will not occur. So the question is, are we going to keep pouring the acid? For us to know the end product or the end point there, for us to know the end point, we need something to tell us that yes, neutralization has occurred. And what's that thing? They are indicators. So to explain this indicator is a bit wide, but it's not really wide, so I'll try to simplify it. So these indicators, they will tell us when neutralization has finally occurred. And what do? They change color due to what? Change in pH value of the solution. We'll call something pH value. We are coming there too. So an acid has a pH value. A base also has a pH value. So the pH value of acid is usually small, less than 7. For base, they have what? Higher pH value, about above 7, maximum of 14. So that will take us to what we call pH scale. So pH scale is number from 0 to 14. So pH scale is got for what we call a pH meter, like something to measure what? The pH value of a solution. If we have a solution and its pH value is 7, it means that particular solution is neutral, meaning it is neither acidic nor basic. Example, salts. All these salts we have here, they are meant to be neutral, although not all salts are neutral. I'm still coming there. So I'm talking about normal salt. Not all normal salts are neutral. So if you now have a pH value less than 7, it is what? Acidic. So we can say acidity increases from 7 to 0, meaning if we have a particular solution that has a pH value of, let's say, 2, another one of pH value 4, the one that has a pH value of 2 is more acidic. And if the pH value reaches 7, it means it is neutral. It is no more acidic. When the pH value surpasses 7, it is now what? It's now alkaline in nature. It's not acidic, it's what? Alkaline. So as we go from here, there is what? Increase in what? Alkalinity. Alkalinity increases. So meaning if I have a base or a solution whose pH value is, let's say, 8, 9, another one whose pH value is 12. So one that has a pH value of 12 is more what? Has more alkalinity than what? The one at 9. So as you move on, as the number gets bigger, there is increase in alkalinity. As the number gets smaller from 7 downward, there is increase in what? In acidity. So what are now indicators? They are weak organic acid or organic base. They are either acidic or basic in nature, but they are organic. So because they are organic, they dissociate partially. So, but the thing is, they are organic, acid or base, and they used to have color, so they're like dyes, and they change color as the pH value of a solution changes. Meaning, suppose I have a particular indicator. When we add indicator inside the base, suppose the indicator is okay. When we add the indicator to base, it shows a particular color. It's going to show a particular color. But as we add acid to the solution, what happens? The pH value will be decreasing. Why? Because for a base, it has high pH. So the color of indicator in basic medium will be different from in acidic medium. So in basic medium, it will show a certain color. And as we are adding acid, what happens? A point to be reached whereby there will be a sharp change. The color will suddenly change. Let's say from maybe red to what? Colorless, or from red to pink, or from pink to what? To colorless, or pink to red. There will be a sudden change. So whenever you have that sudden change, it means the end point has been reached. It means neutralization has occurred. That is what? The advantage of what? Of an indicator, or the use of an indicator. So I explain indicator and how is the pH scale gotten. But before that, let's do what we call qualitative analysis of what? Neutralization reaction. So but before we move on to that, let's revise this. Normally you should have idea about it before. So this N is mole. Mole can be written as what? Mass over molar mass. So or atomic mass for an element. But for a compound it's called mass over molar mass. Now secondly, mole can be written as what? Concentration, or we call it molar concentration times volume. I believe you should know mole over molar mass before now. Mole equals mass over molar before now. So but let me quickly explain concentration very brief. So for every solution, or yeah, we call something concentration. Concentration. And what is concentration? It is the amount of a particular substance present in a certain volume of that solution. Amount of substance to volume. So and this volume is in dm cube. If I have 1 dm cube of, let's say, an acid, what is the number of mole of that acid in that particular solution? That's what we call the concentration. So the more number of mole you have per dm cube, the more the concentration. Suppose we have 1 dm cube of water, and inside we have, let's say, 0.5 mole of an acid. Then we have another solution. In 1 dm cube, we have, let's say, 2 moles of other acid. That one that has 2 moles in 1 dm cube has more concentration. And I think I mentioned something about that when I was explaining concentrated and dilute acid. So it is what? And from here, this mole, the unit of mole is mol, while volume is what? dm cube. So the unit of this mole here, which we call what? Molar concentration, is what? Mole per dm cube. So this is what we call molar concentration. But instead of using mole as amount of substance to volume, we can also call it what? Mass of a substance present in a certain volume. Mass per volume. In this case, this is no more molar concentration. We call it what? Mass concentration. I use this G, representing grams, unit of mass. So this CM is what? Molar concentration, and this is what we call gram what? Concentration, or let's say mass concentration. That's mass per volume. Mass is in kg. Volume is in what? dm cube. Sorry, not kg. This is grams. Then we use gram as the unit of mass in chemistry. If this is kg as SI unit. Why volume here is what? dm cube. So here, the unit of this what? Mass concentration is what? Gram per dm cube. So when we talk about concentration, there are two kinds. We have the molar concentration in mole per dm cube. We have what? Mass concentration in gram per dm cube. And this will have what? Relationship in terms of what? Number of mole, which we have it here. So molar concentration equals to what? Mass concentration over molar mass. Sorry, not mole, to molar mass. So whenever you are given mass concentration, and you know the molar mass of a particular compound, we can get the what? Molar concentration. For example, for this sodium hydroxide, we can look for its molar mass. So if you know its mass concentration in a particular what? Solution, we can look for the what? Molar concentration. So we can say concentration in mole per dm cube equals what? Concentration in gram per dm cube divided by molar mass. The last is this one for gases. For any gas involved during this process, the volume of the gas involved, note, LACV here, V is in what? dm cube. And know that 1 dm cube is equivalent to 1000 cm cube. You should always note that. So at STP, put this there. At STP, the number of mole is what? The volume of any gas divided by what? We call it molar volume at STP, 20.4 dm cube. So these 5 hours is very important. And from here, particularly for neutralization, let's get the connection between what? The molar concentration of acid and base. Let's do that. So we can note what we have here, because I want to clean this one before I move on. Note this, then let's move on. Now let me pick one of these reactions. Let me pick this one here, the second one. Now, for this one, the indicator already told us when the endpoint has reached. And please, when add indicator to the base, ensure you add a very small amount. 1 or 2 drops is okay, so that the endpoint will be sharp. So you can easily note the endpoint. If not, if it's too much, you cannot note the endpoint easily. So, in case they ask, why do you add a few drops of indicator in the base? In order to ensure the endpoint is what? Is sharp. Now, in this particular equation, this acid has a number of mole of 2. This one has what? Number of mole of 1. And now they've reached what? What do they call it? Neutralization. If you are to add 2 to 2 or 1 1, it's not occur. It means we didn't add what? The right ratio. So now, let me use this second point here also. This one here. Now, in this particular reaction, the number of mole of acid, let me call it Na, equals to what? The concentration of acid use times volume of acid use. Yeah. Mole is CV. Concentration times volume. So for acid, I'll call it NaCAV. For the base, number of mole of base is what equals to concentration of the base, volume of the base, because the base will have a volume, the acid also have a volume, a particular volume. They also have a concentration from how they were prepared, and from the balance equation we can get the what number of mole. So from this relation, let's try to divide the right hand side first. So if I divide this with this, I'll get this over this, or if I divide this with this, I'll get this over this. So, but let's try to divide both sides. So in this case, I can say this over this, Ca VA over CB VB, this divided by this, same thing as this divided by this, NA over what? NB. So this is very important. Why? Because in question, let's say in qualitative analysis question, most times you won't be given the volume of residues if it's a real practical. For real practical, you will be the one to determine the volume of residues, meaning they will give you a particular volume of base to use, usually 20 cm cube or 25 cm cube of base. So volume of base is usually known. The concentration of acid and base is prepared by your teacher. You have to prepare the acid and the base to use, following the instruction from WAEC. So for NaNB, you get out by yourself, balancing the equation. From the balance equation, so this 2 is Na, so Na is 2. This one is NB, NB is 1. So you can always get this on yourself. Volume of the base will always be given. You'll be able to look for volume of acid by doing the real practical. So the major thing we want to get from this practical is VA, volume of acid use, which we call it average titer. So most times, in order to ensure that there are not much error, we repeat the experiment like 2 or 3 times. Then we look for the average of the volume of acid use. So we call it the average titer value. So CB, sometimes they'll be given directly, or sometimes they'll be given indirectly. So if they are given indirectly, these are all you need. They can give you the mass concentration, so from there you get what? The molar concentration. So that is it. And in a case when gases are formed, so you need this last formula here. So for titration, always note this. NaNB you get it by yourself. VB will always be given. For VA, if it's real practical, you will get it by yourself. How? After adding the indicator here, you through this step, you release the acid bit by bit, until there is endpoint. When there is sharp change in color of the indicator from a particular color to another, then you note the volume of acid use. That's VA. Or sometimes you can do it 1, 2, 3 times. So you can draw a table. You have the what called the rough titer, the first, second, the third. Then you take the average. But if it's alternative to practical, if it's not a real practical, you'll be given the volume of acid use, either directly or you'll be given a table. From that table, you get VA yourself, looking for the average. So I think with this, we are ready to solve question on quantitative analysis, under titration. So but before we solve question on this, which is, the peak we have to know, let's now go back to the concept of pH scale. How was it gotten? And let's now go in detail, what is an indicator? So please write indicator. So what is an indicator? Right, please. Indicator are weak organic acids or bases which will produce different colors in solution according to the hydrogen ion concentration in that solution. Meaning, as the concentration of hydrogen ion is changing, what happens? The color also changes accordingly. That is an indicator, and they are usually colored also, or we call them dyes, organic dyes. DYES. So on the board here we have 5 indicators. We have litmus paper, we have the methyl orange, methyl red, and phenolphthalein. So apart from these 3, litmus paper is, it's a solid like a paper. It's mainly used to test if a particular solution is acidic or basic. They are not suitable for titration. So not suitable for titration. Now, we know litmus paper in acidic medium, it turns blue to red, while basic red to blue. We know that. Now for methyl orange, in acidic medium, it is red, and it will gradually change towards yellow in basic medium. Sorry, basic medium is going to be yellow. Then methyl red, it is red in acidic medium. They are both red, yellow. Phenolphthalein in acidic medium is colorless. In basic medium, it is what? It is pink. So when are they best used? Now, if you consider this range falls towards pH of what? Of acid, 0 and 7. So these two are best used whenever you have what? Strong acid versus weak base. Same goes for this strong acid, weak base. Whenever you are titrating a strong acid with weak base, you use what? Methyl orange or methyl red. Although they have same color, but methyl red is better. It will give us higher accuracy. Now, phenolphthalein, when you check the range, its pH range is from 8.2 to 10.0, so it falls to basic side. So we use this one whenever we are doing titration of what? Weak acid versus what? Strong base. Example of weak acid, strong base. This is weak acid, strong base. So for this case, we are going to use what? Phenolphthalein. So what about strong acid, weak base? For strong acid, weak base, we can use what? Either methyl orange or methyl red. So what if you have strong acid, strong base? If you have strong acid, strong base, you can use any indicator. We can use methyl orange, methyl red, or phenolphthalein. Any of these three can be used as indicator for strong acid and strong base. What about for weak acid and weak base? None of them. So for the titration of what? Strong acid and weak acid and weak base, there is no suitable what? Titration. We have other ways we can what? Determine the endpoint, and it is mainly because the endpoint will not be sharp. So we can even show this on the graph. If the titration has a weak base, what's the ratio? What will be the graph of the volume needed, per pH? Or we can sketch pH on vertical axis, then the volume of acid used on the horizontal axis, and we can show how the pH value changes as the volume of acid is being added. Now note, for litmus paper, the main reason they are not used as indicator is because they change it gradually from red to purple, then to blue. They have no sharp color, meaning they are not suitable for end point detection. But for this remaining three, they have. Yeah, so we can say the midway color for litmus paper is purple, but it's not sharp. But for remaining, for methyl orange and methyl red, their midway color are both orange, and I will explain. Why for phenolphthalein it is what? A light pink, very light, a light pink. So the question is, what do we mean by midway color? Now, for example, let's take methyl orange. So in case when you have strong acidic base, like in this case, strong acidic base, so the indicator are usually added to the base. So when we add the methyl red, to the base, then it will be yellow in color. That's what it will be yellow. So this base normally is colorless, but after the indicator it becomes yellow. So what happens? You will now keep adding this acid. Then when you get a certain volume, when a certain volume of acid is added, when a certain volume of acid is added, then this yellow, in basic mineral is yellow. As you add acid, it's becoming acidic a bit. The pH is what will be reducing because of what? Increasing hydrogen ion concentration. So the color will try to change from what? Yellow to red. And the midway from yellow to red is actually orange. So if you have to add the methyl red to the acid and pour base to inside, it's moved from red to yellow. But the standard is we used to what? Add it to the base. So the midway between yellow and red is what? Orange. Although for methyl red, the orange will be a bit dark, so it's like a reddish orange. This one will be the normal orange. This one will be very close to orange. While this one is going to be what? A very faint pink, very faint, or we call it a light pink. So that is what we mean by midway color. Now let's now talk more about indicators and pH. So before we move in depth on how indicators actually work, although we are done, so let's talk about pH itself. Now for water, H2O. Water is a very weak acid, or we can call it a weak base also, according to both Lowry and Lewis theory. We've already explained that in our previous class. It can dissociate to give us, H plus and OH minus, and this is at equilibrium. So it can dissociate to give us this, and this will come back here. So we call it a weak acid or weak base because it ionizes partially. Then when the concentration of the ionized hydrogen ion and hydroxide ion are measured, we realize that for hydrogen plus, it is actually what? 10 to the power of negative what? 7. That is 1 over 10 million. That's the concentration of what? Of H plus. While for OH minus, its concentration is also what? 10 to the power of minus 7. So, and if you multiply both of them together, we are getting 10 to the power what? Minus 4. So this indicates the concentration of hydrogen ion, and this indicates the concentration of what? Hydrogen ion. And this, when we multiply the concentration of what? Hydrogen and what? Hydroxyl ion, what we actually get, which is this 10 minus 14, is called the ionic product of water. Ionic product of water. And this value is constant at 25 degrees Celsius at all circumstances. As far as temperature is maintained at 25 degrees Celsius, this is all called the ionic product of water, and it's meant to be constant. So, let's suppose we have acidified water, meaning water whereby acid is added. When an acid is added to water, because for example, let's suppose we add HCl to water. This HCl has H plus. If you have to add HCl, this HCl itself dissociates to give us H plus and Cl minus. So it means we are adding more H plus to it. The concentration of hydrogen ion will now increase, while this one will decrease relatively, because we are adding more of this and we are not adding any of this. So what happens? The water becomes acidic. So instead of the concentration to minus 10 to minus 7, it will increase to, let's say, 10 to the power of what? Minus 5. What happens to the second one? It will what? Drop to what? 10 raised to power minus 9. It will give us our what? KW. So in this case, the concentration of hydrogen plus has increased. This one has reduced. So the water is now what? Acidic this time around. But working with all this will be a bit what? Difficult. So you see this 5 here, this 5 here. We will not give it a name. We understand it to be a concentration, and we know what concentration means. Concentration means what? Concentration means, where is it? Okay, I think it's already. This is C. The amount present per what? Per volume. So if the volume of water is 1 dm³, so the amount present is what called what? Concentration. So if you take 1 mole of water, it contains what? 10 to the power minus 7 mole of hydrogen ion, 10 to the power minus 7 of what? Hydroxyl ion. So this 5 itself is all called pH of water in this case. The pH equals to 5. How? It's simple mathematics. So how can we turn everything here to 5? If I take log 10 to the power minus 5 base 5, the answer will give minus 5. But we are going to minus at the back here. By the time you solve this, we are going to get 5. Why? In mathematics, the coefficient of what is to power to base 10 rather. So this power goes to the back. So if I have log 10 to the power minus 5 base 10, this answer will go to the back, multiply this minus, that will be minus 5 log 10 base 10. Log 10 base 10 is 1. Minus 10 is plus, so the answer is what? 5. So what can we say from here? We can say the pH of a solution is what? Negative logarithm of the concentration of hydrogen ion to base 10. That's what we call what? pH what? Value of that solution. For example, for this particular acidified water, if you want to look for its pH, this is the concentration. We'll put the concentration here, then we'll do minus log, we press it, you can use your calculator straight, and we get what? The pH value. As long as it's obvious here, we always have minus 14 here. This will give us 10 to the power minus 14 here. So it means if you add this 5 and this 9, you must always get what? 14. So meaning if you add the pH, so this 9 is called what? pOH. You must always get 14. So if you know the pH of a solution, it means we already know its pOH. So what will the pOH? 9 in this case. So for an acid, as the concentration is increasing, this number, neglecting the sign, will be reducing. For example, it was minus 7. From minus 7 to minus 5, it's actually increment, not decrease. You might think that 7 is greater than 5. No. Because if you have to write this one, 10 to the power of minus 5 actually means 1 over, then put 5 zeros there. Compared to 10 to the power minus 7, when I put what? 7 zeros there. So when you divide by 10 million, and when you divide by 100,000, which one is smaller? When you divide by 10 million. So mean when the concentration of hydrogen increases, this number, neglecting the sign, will be reducing from 5, or let's say from 7 to 6 to 5 to 4, it will be reducing. And as this one is reducing, what this one, it will be increasing. And that is why for pH, as the pH value is decreasing, it means its acidity is increasing. And as it's increasing, the acidity is what? Is reducing, or the alkalinity is also what? Is increasing. So in case if you ask, what is pH value? So pH value of what? Of an acid or of a solution is what? Negative logarithm of what? The concentration of hydrogen ion to base 10. So please note this. And sometimes if you give a question whereby you have to deal with what? Concentration, pH, and the likes. What you need to understand before you can solve any question on this is mathematics, logarithm. If you understand logarithm very well, you have no issue here. So I'm going to take an example on this. Now, lastly, back to the question. How do indicator, why they change color? How does it happen? Let me just explain that briefly. So indicators are weak organic acid or base. So let's consider a particular indicator which is an organic acid. So that indicator is going to have the cation part and the anion part. So it will have a cation and anion. So let's make that HIN. So H is the cation part, is plus, ion is going to be minus. And this can dissociate to give us H plus and ion minus. This sign is like indicator, It's like if you have something like HCl, I'll write as H plus, Cl minus. This arrow means it can go both ways. Now, suppose if you have, let's say, 1,000 molecules of a particular organic acid, which is an indicator, how about that 1,000? About 10 of them is what will ionize. The remaining will not ionize. So out of 1,000, let's say 995 did not ionize. Only 5 ionizes. So the color of this 995 and the color of these 5, they are different. So those that ionizes, they have different color with what? Those that do not ionize. Now, checking 5 versus 995. What happens? At the end of the day, the color of this one will overshadow that of this. The color of this will overshadow that of this. But if we have more of this and less of this, the color of this will overshadow this later. And that is how their color changes. For example, phenolphthalein. For phenolphthalein, it's actually colorless. It has no color. Phenolphthalein molecules have no color. But when they dissociate, this particular one has like a pinkish red, or let's say like a red color. When it dissociates, this is actually what? This negative part is red. Now what happens is, if this phenolphthalein is added to a base, suppose we have sodium hydroxide as a base. Sodium hydroxide. So here we are having Na plus and OH minus. So what happens here is, these two will come together to form what? Water. Now, this cellular system is at equilibrium, meaning the amount of this phenolphthalein turning ionizing because the amount of this ions turning back to the molecule, it is balanced. But this time H plus is used up to produce water molecule. We are using H plus. Now we call something Le Chatelier's principle under equilibrium. So when the particular system is at equilibrium and one of the factors that keeps it at equilibrium is altered, then the position will shift. The equilibrium position will shift. Meaning, if you take this out, the position will shift to the right. Meaning, more of what? H plus is going to be produced. So out of this 995, the number of what the molecule will be dropping, let's from 995 to let's say 700 or thereabout, it will be dropping, while this will be increasing. So at the end of the day, the color of this will overshadow this. So red will overshadow the colorless, and that is why at the end it becomes pink, like a pinkish red, like a diluted red. So that's why it changes. So if we add a base to it, H plus will be used up. So because we are using H plus up, more H plus is going to be produced, and the color of this one will overshadow the colorless. Then what happens? The color of that indicator changes from colorless to what? To red or to pink. If we are to add an acid to it, so a base to it, for a base, it doesn't have what? Sorry, if you are to add acid to it, acid doesn't have OH. So for example, if you are to add, let's say, HCl to this phenolphthalein, this HCl has H plus and Cl minus. What happens is we are adding more H plus. As you are adding more H plus here, what happens? The position will shift towards to the left. So you are going to produce more of what? Phenolphthalein molecule, which is colorless. So before it was 995 to 5. What happened now? This one will be reducing further. What happened is going to favor the colorless what? Solution. That is why phenolphthalein is colorless in acidic medium, and it's pink or red, or let's say pinkish red in basic medium. That is simply it. Same goes for methyl orange and methyl red. And I believe to a large extent you understand how indicators work. Okay, when I started the lecture, I gave examples of strong acid and what? Weak base and strong acid. Let's give the examples again. For the first one, here we have strong acid and we have weak base. So the end product is going to be, NH4Cl with H2O. For this one, we are going to have this with this. That's Na2CO3 plus H2O. So let's balance up 2 over here. Is that balance? And then it becomes, why for this one is balanced. To balance up 2 has to be here also. Now, these two salts are normal salts, yes. But this particular salt is acidic in nature. Another salt is alkaline in nature. Alkaline in nature. Why? How first? If you have to use a litmus paper to test ammonium chloride, it will act like a base, meaning if it's red, it will turn into blue. This one, sorry, it will turn into red. If it's blue, turn to red. This one, if it's red, turn into blue. So this sodium carbonate will act like a base. In fact, in some titration, they can titrate this with an acid. Why? Whenever we are having strong acid or a weak base, it means we have more ionized what? H plus here, and we have less OH minus. So at the end, we have excess H plus. That's why in this solution, it acts like an acid, acidic. For this one ionized partially, this ionizes what? Completely. So here we have more OH and less what? H plus. So at the end, because of the excess OH, the solution becomes what? And this will lead us to what we call hydrolysis of salt. If you have strong acid and strong base, the salt you are going to form will be neutral to a litmus paper. So in this one, it will have a pH that is less than 7. This one will have what? A pH greater than what? 7. Let's take a strong acid like HCl and a strong base like what? Sodium hydroxide. At the end, we have sodium chloride and water. This other sodium is neutral. It's going to be neutral because we are having strong acid and strong base. So we have excess H plus, excess what? OH minus, and at the end we have what? They will form water molecule. So this one is going to be what? Neutral. So meaning among the normal salts, some of them can be acidic in nature, some can be what? Basic in nature, depending on what. So if we add water to sodium chloride, normally what's meant to happen is that the sodium chloride will only be hydrated. It will be hydrated. Not to happen. It's not going to reverse. But for this, if you have weak salts like ammonium chloride, so I say weak salt, acidic salt, and we add water to it, what happens? It will be like a reverse of neutralization. So at the end of the day, we are having NH for OH plus ACl. For this one also, if you had to add, this to water, we'll be having NaOH plus H2CO3. So these are called hydrolysis of salts. Hydrolysis of salts, like a reverse of neutralization. But it's not all salts that can undergo hydrolysis. There are salts that are formed from either strong acid and weak base, or weak acid and strong base. But for the salts formed from strong acid, strong base, they do not undergo hydrolysis. So most salts do not undergo hydrolysis. So we can classify salts into two: salts that can undergo hydrolysis and those that cannot undergo hydrolysis. So lastly, under acids and salts. So the way acid, base and salt react with their environment differs. There are some that give out their water of crystallization. Yes. And some they absorb or they take in water of crystallization, or let's say moist or water vapor from the surrounding. So those that give out water of crystallization, they are called efflorescent compounds. Those that again, they are either deliquescent and hygroscopic in nature. So please, I want you to go and read on efflorescent salts or efflorescent compounds. Yes, hygroscopic and what? Deliquescent. Very simple. Know the examples and when they are used and how they are used. So some are used as drying agents, some for dehydration agents and the likes. So read on efflorescence, deliquescence, and hygroscopic. So or hygroscopy under classification of ionic compounds. Now we have different kind of indicators. Apart from what we call the pH scale, we have what we call the universal indicator. As for the case of universal indicators, they are made up of a mixture of various indicators which work at different ranges, So we have them working together, to have a. So although for a pH scale they are more accurate, but most times universal indicators are used. And I'll end this lecture by talking briefly about buffer solution. Buffer solution, in case you are asked, what are buffer solutions? Before I explain what buffer solutions are, so note this: if we have a particular solution, and let's suppose we are having 1000 cm3 of a solution, and the pH of that solution is, let's say, 5. Meaning it's acidic, that's the pH. If we add a little acid to it, or a little base to it, what happens? No matter how small, even if you are to add, let's say, 5 cm3 of acid or base, the pH will change drastically. If you add 5 cm3 of an acid, it can change from 5 to, let's say, 2. You are adding a little amount and the pH is changing drastically, and this effect can be dangerous in nature. And I will explain. For example, for human body, our blood, we have blood, and our blood also have pH. And the pH of our normal blood, it should be around 7.4, between 7 to 8. So if you consume something, and that thing has a pH value of, let's say, 2, no matter how small, what happens? Your pH value will spike. It will reduce drastically from, you're adding particular acid. No matter how small it is, the pH will drop from like 5 to 2, which is too acidic. Same goes for plants also. For example, most plant grows when the pH of the soil is between 7 and 8. But if the pH value of the soil drastically changes from, let's say, 8 to like 3, or from, let's say, 8 to like 10, what happens? The plant will not grow again. So in this case, in order to avoid this, we have particular solution, they call them buffer solution. And what are buffer solution? So buffer solution are solution that resist changes in pH on dilution or on addition of small amount of acid or alkalis. When a small acid or a small alkali is added to a solution and its pH resists to change, That's what we call a buffer solution. And what are they, or how are they made? So they actually consist of a weak acid or a weak base in the presence of one of its salts. The salt of a weak acid with that weak acid mixed together, or a salt of what, a base mixed with that base together, will give us what, buffer solution. And they have great importance in medicine and in biochemistry. So when pH value are often critical to what, to be maintained at a steady value. So if you want the pH to be steady with, let's say, a variation of, let's say, plus or minus 0.2 or 0.5, so what we use are what, buffer solution. Examples, let's take some examples. For example, these two are weak bases and these are also weak acids. So if we add to aluminum hydroxide, we have, let's say, aluminum chloride. If we add to, let's say, this ammonium chloride, and here let's suppose we add sodium carbonate, and to this one we add, let's say, sodium ethanoate. So this is what we call a buffer solution. These are buffer solution. So we have a weak acid with its own salt. So a weak base with its own salt, or a weak acid with its own salt. These are what we call buffer solution. In this kind of solution, if a little acid is added or a little base is added, the pH will resist change. It will not easily change. So I think with that we can end this lecture here. The last thing is just for us to solve question in general. Thank you very much.